Coming to step 3. See, a proton is abstracted from this to give the final product. For the abstraction of proton, we will be using the solvent again, but now it acts as a base. Okay, then we get this final product. Let us check the configuration of this. Yes, first rank, second rank, third rank, and then this is fourth rank. Now going from first to third, see, we are going in clockwise direction with the least priority group is with the dash. So therefore, the absolute configuration can be given as R here. Clockwise, and the least priority group is with dash. So is R. Now let us take the other one and check. Now in this case, okay, the same thing again. Now let us check the configuration. Carbon to oxygen, rank 1, carbon to carbon, but again this carbon is bonded to some other carbon, so rank 2. You know how to give ranking. Now going from 1 to 3, we are going in anti-clockwise direction with the least priority group bonded by dash. So the absolute configuration can be given as S. Okay. Now let me tell you the most important point in this case. See, we have actually started with S isomer. So we end up with, of course, a racemic mixture, but with more of R than S. But why? We'll tell you. If suppose we start with R, we end up with more of S than the R. But why? So this is actually called stereoselective or stereoselectivity, wherein, of course, we get a racemic mixture. I mean, we get both the isomers, but with more of inversion product rather than the retention product. Let me now tell you why. See, I told you that in SN1, initially the alkyl halide undergoes ionization to form a carbocation, which is planar, sp2 hybridized, and is attacked from both the sides. But this attack will be less from the direction of the leaving group. Look at this. See, supposing if this is the direction of the leaving group. Now, if suppose the nucleophile is trying to attack from the same side, it will have some obstruction. So this possibility is of course less. But if the same nucleophile attacks from the rear side, from the side opposite to that of the leaving group, you don't have any obstruction. This is okay. So if suppose it attacks from the same side, you get something called retention product. Yes, because if suppose you start with S, you will end up with S. I mean, your configuration is retained, so is called retention product. Now, if suppose the second one is considered, that means the backside attack. If this is frontal or front side attack, I mean from the side of a leaving group. This is your leaving group, LG. This will give us a retention product, and that will of course be very less because of the obstruction that it experiences in getting closer to the carbon atom or the carbocation. Now, attack from the rear side. This, of course, will result in inversion of configuration. I mean, if you start with something having S configuration, you will end up with R configuration. But because you don't have any problem in attacking the carbocation from the rear side, I mean, as you don't have any obstruction, this inversion product will be more. So that is what I'm telling. If you start with S, no doubt, you end up with both R and S. But more of R rather than S. Same is the case with R. If you start with R, you'll end up with S, which is more when compared to R. Similarly, you can even consider this. Supposing if you start with a cis isomer, trans is going to be more when compared to cis. You get both, but trans is obtained with more yield than the cis one. If you start with trans, you will end up with, it's a regular point, not in this. Cis will be more when compared to the trans. This is what we call stereo selectivity, right? We get both, but one is formed as a major product than the other one. Then this also is called stereo selectivity. Okay. So this is very, very, very important as far as SN1 is considered. Remember, more of inversion product rather than retention. Now, some other important points. You know, in case of SN1, rate depends on the concentration of alkyl halide, not on the concentration of nucleophile. So order with respect to alkyl halide is 1, and that with respect to nucleophile is 0. So overall order of this reaction is first order. So I can tell you that SN1 follows first order kinetics. Okay, next. See, in the rate determining step, only one molecule, I mean the alkyl halide, is participating. So, yes, we call this a unimolecular reaction. Okay, in terms of molecularity, we call it unimolecular because there is only one molecule participating in the slow step or the rate determining step of the reaction. Okay. Next. As far as the reactivity order is concerned, you know, the SN1 reactivity can be given as directly proportional to the stability of carbocation. As the intermediate in SN1 is carbocation, and moreover it is formed in rate determining step. So greater the stability of carbocation formed, greater is the SN1 reactivity. And we know that the factors which stabilize the carbocation are hyperconjugation and plus sign. Carbocation is stabilized by these two. Okay. Now, as the intermediate is carbocation, rearrangements are very much possible. Let me give you an example. See, when neopentyl bromide is taken, in the first step, that is ionization, when bromide is lost, we get this particular carbocation. Which is of 1 degree type. Now this, because it is a less stable, it undergoes a rearrangement. Yes. One to methyl shift, which results in this particular carbocation. Recall your memory of what you have seen in E1. See, this is a 3 degree carbocation which is more stable than 1 degree. Okay. Now this 3 degree carbocation is what is attacked by the solvent, which of course is a weaker nucleophile, because here the rate is independent of the concentration of nucleophile. We can go with the weaker nucleophile. In fact, we are going with a solvent which acts as a weaker nucleophile. Now, the pair of electron is given to the electron deficient carbon, right? Now, this will give us let me just give you the product straight away. It's not a chiral one, so we are not going to discuss about that factor here. Okay, this is what we get. Just a second. Because a pair of electron is donated, we get a positive charge. Now the last step. See, here it has acted as nucleophile. Now we are going to take the same solvent which will be acting as a base. See the difference? Now this pair of electron is given to an electron deficient proton. This will give us the final product. This is what we get. Okay. It's an ether. So this is how rearrangements occur. Now, as I said, SN1 reactions require a weaker nucleophile. It is because rate of SN1 reactions is independent of the concentration of, yes, nucleophile. Most of the cases, solvent itself acts as a weaker nucleophile. So, a weaker nucleophile is sufficient enough to carry out SN1 reaction. Then, let me give you information regarding the leaving group. See, a good leaving group is what we require. But what is a good leaving group? Let me give you an example. Consider these two. You know, HCl is a strong acid, whereas water compared to HCl is a weaker one. Okay. When HCl loses a proton, we get Cl minus. And when water loses a proton, we get OH minus. See, the conjugate base of a strong acid is weak, right? So this is a weak conjugate base, whereas the conjugate base of a weak acid is strong. So this is a strong conjugate base. What do you mean by a strong conjugate base? Means it is a strong proton acceptor. a strong proton acceptor, whereas onto the other side, this one being a weak conjugate base is a poor proton acceptor. Let me explain the same in a different way. Now coming to HCl, which is a strong acid, you know, it has great tendency to lose a proton. So the resultant Cl minus, is happy without H plus. Of course, that is what is given here as poor proton acceptor. Yes, it is happy without H plus. And see, even after leaving in the form of Cl minus, it will be happy. It will be stable. So it will be very much ready to leave. So is a good leaving group. On to the other hand, see, water is a weak acid. What do you mean by a weak acid? A poor proton donor. Doesn't want to lose a proton. But still, if a proton is removed and if suppose OH minus is formed, it will be waiting for H plus. It will be waiting for a proton to come to it. So is a strong proton acceptor. It is very much unhappy about leaving. OH minus is not that happy as chloride. OH minus now will be waiting for H plus to come. So it is not happy, not so stable as a Cl minus, and so is not a good leaving group. Let me say a poor leaving group. Okay. Remember, a good leaving group is some species which leaves as a stable one, just like our chloride, leaving happily, leaving as a stable one. So if the basic strength of the conjugate base is less, it will be a good leaving group. So let me just give you here that the leaving group ability can be given as inversely proportional to the basic strength of conjugate base. Okay. So if the basic strength of the conjugate base is more, I mean, if its proton accepting tendency is more, it will be a poor leaving group like our water molecule. Earlier in elimination reactions, we have taken a very good example of HF, HCl, HBr, and HI. You can check that out. Okay. Now, let me give you examples for the leaving groups. I mean, the better ones and the best ones. Look at this. So this is paratoluene sulfonyl chloride. also known as tosyl chloride. It's a better leaving group. Means once it loses the chloride ion, it gets better stabilized. Remember, if something is going out, the one that has gone out has to be happy, has to be stable. Even the one that has lost it must also be stable. Then only it is said to be a better leaving. Now, coming to one more example. This is very interesting. So this is called trifluorosulfonate ion, also known as triflate ion. Okay. It is, of course, known as a super leaving. Triflate ion. It is actually formed from the strongest acid, trifluorosulfonic acid. Strongest acid will have a weakest conjugate base and will be happy even after losing a proton. So that is the reason why it has become the super leaving, right? So this is about the leaving group ability.